All right. So, hey. Look, I admire all of your efforts on the, I'm going to leave this pile here so that people can pick theirs up. But all of you got basically 30 points just for coming and sitting here and trying. And that's kind of the theme of this class. I want you to realize, like, I'm not going to grade you very harshly in this class. If you show up and you put in the time and effort, you'll pass. And then you'll distribute you know, among grades. Most people that take this class get an A.
So you're saying our actual grade is 30 points less than what we got?
Well, no. That's about what. No, grading is always a fluid thing, and it's the way that I graded. But what I did was I just graded each. If you want to know, if you're curious, I only graded the A, B. I didn't grade the C. That was the bonus question. And for the A and B, I've made them each where I could subtract up to 5 points per of those questions, and that's where I get that there's 70 points I could take off. But no one handed in an empty test and took home 30 points, so it's fine, don't worry about it.
You could have done that?
Well, I guess in principle you could have, but nobody did. So anyway, don't worry about it. And it's 20% of your total grade, so it's really not a big impact. It's just a quest to get you to review the homework solutions, which many of you did. So, all right. So what we're going to do now is we're going to shift gears. And this is going to be much like what happened in the general relativity class, where in the general relativity class we spent the first part of the semester developing the formalism of Einstein's equations. We introduced transformations and variants. We introduced tensors, we introduced curvature, covariant derivatives, all this stuff, and we eventually just wanted to write down what Einstein's equation was. And then we spent the rest of the semester solving Einstein's equation or exploring solutions to Einstein's equation. And that sounds kind of boring, but that's where it actually gets super sexy, because that's where you start talking about black holes and cosmology and all the stuff that really gets people going. Similarly now, yes?
So is this where like the textbook 2 starts?
Part?
Oh, I have no idea. I don't remember. I don't remember, but possibly. Yeah, you can figure it out. But anyway, so this course now we've sort of developed the formalism of the underpinnings of the standard model. In particular, we talked about how we introduce symmetries through taking a global symmetry and demanding that it be locally invariant. We talked about the problems with mass terms among particles and gauge particles and how the Higgs mechanism solves that. So what are we going to turn to now? What do you think?
I was going to say, like, trying to extract information from the equations themselves.
Well, no, we're going to do calculations. We're actually going to figure out what kinds of things should a particle physicist calculate so that experimentalists can take their data and compare.
That's what I was trying to say.
Okay, well, you should have said it more cleaner. It's fine. So, but no, but seriously, so the track of what we've been doing is going to change rather significantly. It's all based on what we did, but it is going to change significantly. So if you've struggled with what we've done before, that's okay, because we're going to kind of lop it and we're going to careen down a different track. We're going to do Feynman calculus. Okay, we're going to do the Feynman diagrams, and that's the backbone of the calculations. And so it's a very different experience than what we've been doing. All right, so first and foremost, I have to point out a couple of things, and that is that almost every reference on calculations, including the Feynman calculus, use a different set of conventions than what we've been developing. We have used conventions that I am the most comfortable with. I'm not a particle physicist. I'm a string theorist, so I kind of lean towards... Oh, great. They're going to be clap. I don't know what the hell's going on over there. Something's going on. Yeah. But anyway, so I'm a string theorist, so I can kind of balance between the conventions. But for example, with the metric, I always preferred the metric to be -1, 1, 1, 1. Can anybody explain why I would prefer that form of the metric over this form of the metric?
Because it only has one -1 as opposed to 3.
Why is that better?
Because I like it.
More contrast.
There's less things to carry around. And like,
Gabriel.
As someone who now has to deal with some of these calculations, if you do the determinant, you always have a minus.
Exactly. When you're doing calculations, often you are forced to take the determinant of the metric. More interesting metrics are G. But anyway, you have to take the determinant of the metric as part of the calculation. And what's the determinant of that metric? What's the determinant of that metric? What if you're in 5D? If you're in 5D, what's the determinant of this metric? What's the determinant of this metric? Still -1, damn it. So it's because I did string theory and I had worked in different numbers of dimensions, but this always having the same sign was useful. So I was like, why don't we do this? And they're complete conventions. Both of them are perfectly, equally valid ways of doing it. It's just things remain constant. Well, guess what we're going to shift to?
No.
We're going to shift to this metric.
No.
Sorry. This is the form of the metric that is most often used by particle physicists. It is in all reference books. I don't know what you guys look up, if you look up things on Wikipedia to get help on your homework or whatever. But I could rewrite the course using -1, 1, 1, 1, but then the only resource that you could use for any help is my notes, because everything else uses this, and it's not always obvious where this impacts things. So various things will change. For example, if I have a vector with components v0, v1, v2, and v3, and I would like to form the invariant, then the invariant is going to take the form v0 squared minus v1 squared minus v2 squared minus v3 squared, where forever we have always said that this would be minus v0 squared plus plus plus. Okay, because what do? You use the metric to turn this into v lower mu. But now the metric is changing the signs of these three instead of changing the sign of that one. So when you put them together, it's now this, okay? And as you might guess, this is also going to change the equations of motion, just a tiny bit. It's usually signs. But the Lagrangian for the Klein-Gordon is now -1/2 MC over h bar squared, phi squared. C psi bar gamma mu d mu psi minus MC squared psi bar psi. Jeez, writing like a maniac up here. Oh, by the way, for those of you who haven't heard, I had a clean MRI this weekend, so. Really, was that like a performance? And my brain was empty!
Well, you did a good job, obviously.
Thank you. I really appreciate it.
Good job at not growing my
Yeah, it's actually a failure, I'm trying to garden in my brain and it didn't work out so good. So, but anyway, yeah. But thank you very much. Okay, so our equations in motion shift just a little bit. So just write those down, or you can go back and look at the notes that are posted online. But and you can compare those to the versions of these equations and Lagrangians that I gave you earlier in the course. But going forward, everything is going to rely on these versus the old versions. Yes?
You said at some point in time that things were going to start, like we were going to start making C and H1 and such. Is that happening soon? Because this is annoying to write out.
Well, actually, we're going to spend a lot of our time calculating something which doesn't really involve C and H. So, yeah, don't worry about it. Well, no, actually, I mean, now is when we can't set C and H equal to 1, because when it does appear, you need it, because you're doing calculations to get numerical values to compare with experiment. Okay, all right. So, we know what is going to shift, and we'll see this later on, but for now, we're going to get our feet wet. Well, actually, we're going to get our feet wet next time. So today what I'm going to do is I'm going to answer the question of what could we calculate to compare with experiment, and what does the calculation look like? And what we're going to find today is that the calculation is a pretty standard expression with one little nugget of unknown in it. And then that little nugget of unknown is what we're going to learn to attack next time using the Feynman diagrams. So we're not going to do a Feynman diagram today, but there'll be a thing in there that I'm like, okay, we'll figure out how to calculate that next time with Feynman diagrams. But what are we going to be interested in calculating? Well, first of all, this is particle physics, so you're interested in calculating quantities associated with what particles do. What do particles do? They move around, okay? So if I got a particle that's doing this, that's not really interesting, right? You know, particles are just doing this. They're moving on straight line trajectories. Like, what's going to make them do something interesting? Interact with another particle, okay? So if you want to have particles interact, what is it you really want to do? You want to take particles and you want to slam them together. You want to create collisions, and then you want to watch for what comes out of the collision, okay? There's one more thing. It's kind of like a collision. What is that? Say it again?
Decay.
Yeah, decay. In fact, those are the two things that we would like to consider. We would like to consider decays and collisions. Okay, decays are simple. You have one particle to begin with, and then you have more than one particle to end with. For collisions, honestly, you could talk about colliding 3 particles, but that's not really that common. You usually just collide 2 things. So we're really either talking about starting with one object, decays into several objects, or you collide 2 objects, and you might have 6 objects come out of that. Okay, and hopefully you remember, because this is a relativistic quantum course, that in relativity particles can appear and disappear. So just because you're slamming an electron and an electron together does not mean that you have to have an electron and electron come out. You can have lots of things come out. Okay, so we're going to talk about decays, and we're going to talk about collisions. So I'm going to write some words up here to sort of lay down some of the ideas in both of these, and then a little later on we'll turn to equations. So for decays, what we have in mind is that we have particle A, for example, and A could possibly decay by many routes. It's not that there's only one method or one end products that A could decay into. So for example, A could decay into particles B plus C, or maybe it could decay into particles D plus E, or maybe it could decay into particles F plus G plus H, and this list just probably goes on and on and on. For each of these, we can calculate, and we'll learn how to do it, a decay rate associated with each of these processes. So we could instead close our eyes and say, what is the probability that A decays, or what is the rate at which A decays, and that is not asking what's the rate at which it decays into this pair, which is this gamma 1, but rather what is the rate at which A decays, period. And that's really simple. It's just governed by a decay rate, which is the sum over all of the decay rates. Okay? So the gammas here are decay rates. They are the quantities that we would want to calculate, okay? And in words, this is the probability per unit time of decaying into, and I'll just say gamma I, into whatever you're picking. So if you're calculating gamma 1, it's decaying into B plus C, blah, 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 blah. Yes?
When we say time, do we mean like time, or do we mean like proper time, since we're doing something kind of relativistic here, like?
No, so we can, well, we'll set up a coordinate system and we'll, have t, x, y, z, and then we'll just use t.
Okay.
Yeah. Okay, so a quantity which is somewhat related to this is, first of all, if you want to know about the change, so if I start with a collection of particles, then the change in the number of particles is proportional to the total decay rate. So we don't care what they decay into, we just care that they're decaying, and we want to know the total rate at which those particles are disappearing, times the number of particles, obviously, times the time interval, okay? And we can take this, and we can solve it, and we find that the number of particles as a function of time is the number initially, times e to the minus gamma total times t. Okay, you could do that in 1 or 2 lines. I know you're all comfortable with solving differential equations. And then this gives us an estimate of the average half-life, which is actually the time at which our population of initial particles decreases by a factor of 1 over e. And this is what we also refer to as the lifetime of the particles. Okay? We're not necessarily going to be after calculating this, but it's a common quantity spoken of by experimentalists, and so I just want to throw that out there. So, in case you're wondering, we're rarely, if ever, going to really try and calculate all of these. I'm just going to show you how to calculate each of these, and then if you ever needed to calculate gamma total or the lifetime, then you should just realize, oh, I just, I go through all the possible outcomes, I calculate all of these, and I add them together. Okay, so does this part of the story make sense? Because the hard part is calculating each of these. That's what we're going to spend our time and money on. Yes, Madison?
Are there not sort of an infinite number
Yeah.
of things? So.
Well, no, it's not infinite. Okay, it's not infinite. No, it actually, well, yeah, it could be infinite. It could be infinite. Yeah, I was going to say, if everything had mass, then it would definitely not be infinite. Because if something can only decay into things that are less massive than what you start with, because you can't gain mass through decaying. Okay, so if you take a particle and all the things it can decay into are massive, then you can only decay into things that add up to less than your. So there's a finite number of results. But unfortunately, we have a lot of massless particles, and you can decay into 1, 2, 3, 4, 12 million of them. Okay.
So no one's generally going through and calculating every single.
No, because what you'll discover is that the contributions vary significantly. So the more basic outcomes have a lower, and so we'll see this when we start doing calculations, but if you pick 600 particles, the decay rate into 600 particles is going to be negligible compared to the smaller number of particles. Yes?
So you can have an infinite number of outcomes, but does the total rate need to be finite?
Yeah, no. But well, just because you have an infinite number doesn't mean that this is going to add up to infinity.
Right.
Yeah.
But in general, with the decay rates?
Yeah, the decay rates have to be finite. Yeah, definitely. Okay. Any other questions about decays? Okay, so the alternative are collisions. And so for collisions, we're thinking of the likelihood of a particular collision event. So, A plus B goes to C plus D. This is the outcome which we'll index by I in the same way that we index these by I. Okay? And the quantity here was the decay rate. In this case, has a cross-section. Sigma I. And then, of course, we can figure out the total cross-section by summing over the cross-sections of all possible outcomes. Okay? That's the same strategy that we had up here. We will learn how to do these calculations for one outcome at a time, and then if you want to know the total cross-sectional answer, okay, that's the question of, I'm going to slam A and B together, what's the probability that anything happens? You have to add them all together, and that'll give you the total cross-section. And in terms of what cross-section means, so, you know, here's a sort of a definitive interpretation of what decay rate means. I mean, decay rate almost means something intuitive, but the lifetime of a particle is a pretty important, you know, thing. You know, how long do we expect the particles to stick around? Well, their lifetime is about 1 over the total decay rate. So what is cross-section? Well, you can think of cross-section literally in terms of shooting arrows. That's a pretty good arrow, I must say.
I'm proud of you.
Man, I'm sobering up. It's not that I just screwed it up. Okay, well, that's an arrow. Okay, shut up. Here, I'll color this in so that it looks a little more. Okay, I'm done. I'm done. Sorry. You know, I was shooting an arrow at a target over here, which of course has to be a bullseye. Okay? Then I would ask you the question, oh man, I haven't even got the cards out today. God, what is wrong with me? You guys are just letting me get away with it.
You haven't pulled out the cards nearly as much this semester as you did last year.
What?
You haven't pulled out the cards nearly as much this semester as you did last year.
Well, I'll fix that right now. Madison Squirt's on top. Madison Squirt's. What's the cross section?
Probably the area of the target.
You are so smart. Yes, sigma equals the area of this thing. Okay? Is it really the area?
You tell me.
It's the area that is exposed to the arrow. In essence, the area that is normal to the flight direction.
Yes. What if I took the target and flipped it up so it was facing up? What would the cross section become? For hitting the bullseye? 0. Yeah, so it's actually, you know, it includes an angle, okay? But anyway, so this is the very primitive idea of cross section, but it's roughly the idea of what we have in mind here. But there are some differences. For example, we are dealing with a soft target. And what I mean by that is, one way to model collisions in this case is to think of, you know, you're shooting an electron at another electron, and the electrons, they're never actually touching each other. Rather, they're interacting with each other's electric fields, and so they're, you know, so it's not like you can point to the edge and go, if you hit here, you're going to get it. If you hit here, you're going to miss it. No, it's more vague than that, okay? So it's an interaction with a potential. What we find is that the answer for the cross-section actually depends on what arrow you're shooting it with. I mean, after all, if you want to hit an electron, if you shoot another electron at it, you'll get one cross-section, but if you shoot a neutrino at it, you'll get a very different cross-section. It's the same thing you're aiming at, but it's a very different cross-section. Okay, that's because a neutrino interacts with an electron very weakly compared to electrons interacting with electrons. The answers are velocity dependent. Okay, here the answer to the question had nothing to do with how fast the arrow was moving. Okay. In these questions, though, that we're going to explore, it's actually going to depend on the velocity. And and then we have more outcomes than hit or not hit. Okay, in this case, it's just you either hit it or you don't, and that's the end of the story. However, in collisions, we can have different particles come out, we can have different configurations. It's a more varied set of outcomes that we need to explore. So again, we're going to focus on learning how to calculate that, and then you can take that and you can figure out the total cross-section just by adding up the cross-sections for all the possible outcomes. But in terms of cross-sections, there's actually one more degree which is important, and that is that when we're studying collisions, or we're actually comparing the experimental results of collisions, what we find is that you sometimes can't just slam a particle into a particle and observe all the angular distribution of outcomes. Okay? Rather, what we end up calculating quite often is for some solid angle, which I'm going to define theta from the horizontal axis, but we might want to know what is the differential cross-section. Okay? And this would basically tell us, what the likelihood of the collision is, for outcomes, going in this direction. And this would only be a function of theta. You would expect it to be symmetric for rotations around this axis, but non-symmetric for rotations on this axis, because this is the axis along which the particles are coming in and slamming into their targets. Okay. All right, so you ready to see the big, the ugly, the nasty? I'm going to give you expressions for gamma i's and sigma i's right now. Let's just do it. All right, let's get dirty. All right. So, yeah, I think I can erase all this. I'll probably regret it, but I'll erase it. All right. All right, now, to be 100% honest, I'm not going to derive these expressions. To derive them would require teaching you quantum field theory. This is not a course in quantum field theory. So, I mean, what I taught you at the beginning of the semester was definitely involved in everything, but the tricky part to getting to where we're going to go now is quantization of everything. And unfortunately, this is not quantization as per physics 320. This is quantum field theory, which is a whole new level of complexity. So what I'm going to do is I'm just going to give you the final results of quantum field theory. And you're going to get comfortable with doing calculations with them because they're not that hard, okay? And I'm going to give you as many interpretations as I can so that you'll look at these expressions and be like, well, I don't know where it came from, but it kind of makes sense that it is in the final answer. But I'm skipping over a very large step right now. It's called quantum field theory. Just kick it to the curb. Okay? All right. So with that in mind, in both decays and scattering, the likelihood of an event, okay, so what I mean is, the likelihood that this particular event is going to be the outcome of a decay. You're going to decay into B plus C or D plus E or whatever. What's the likelihood of B plus C over D plus E? Or the outcome of a scattering event. What's the probability or the cross-section associated with two particles slamming into each other and outcomes B plus C or D plus E or whatever. So the probability of a set of events actually has two very important factors which go into determining them. A, it's kinematics. So is impacting the outcomes of certain things. So kinematics is the first, which is associated with phase space degrees of freedom. And the second is dynamics. Okay? So what do I mean by kinematics? Well, it turns out that there's many different parts of the expressions I'm about to write down which capture that kinematics plays an important role. But just to give you an idea, as an example, which I think many of you have probably seen, when we are determining the likelihood of an outcome, one of the things that we have to realize, so I'm just going to do a decay. So if this particle A is going to decay into particles B plus C, or particles D and E, here is one, not all of them, but one of the impacts that kinematics have, and that is the following. Suppose that MA is much larger than MB plus MC, and MA is only slightly larger than MD plus ME. Okay? So remember, you can lose mass in a decay because all that needs to be conserved is the square of 4 momentum. So you can translate mass into energy, which also shows up as momentum. Okay? So what you start with in terms of mass is certainly not what you need in the end. In fact, if you try and decay into something that has exactly the same mass as what you start with, the rate will be 0, always. But which of these two situations do you think is more probable?
Probably the one with
I'm actually going to draw a card. Hunter. You're the only hunter that's here today. Which do you think is more probable?
I was thinking of the one with the closer mass. So you.
The one with the closer mass? Why?
I was just thinking, like, you're reverting your mass to energy, right, in the decaying process. So you probably go to the first stable thing.
Yeah, that's a pretty reasonable answer. Like, A is closer in mass to this than this, and so less has to happen for A to decay to this than to this. Okay? It's exactly wrong, but it's a good answer. No, and it's fine. That's fine. I mean, look, not all of this is intuitive. So one of the things that we're going to discover is that in the formulas that I'm going to write down, one of the parts of the calculation is summing over possible outcomes. So what are the outcomes of this? Well, this comes out with some momentum, and this comes out with some momentum, and this comes out with some momentum, and this comes out with some momentum. And we have to sum over all of the various momentum, that these come out with or whatever. Actually, I should say there's another particle in here. This is particle F. And this is particle G. And I was too restrictive of myself when I did this with 2 particles. And you'll understand why in a little bit. But anyway, okay, so it's the same scenario. So what we discover is that we have to take the energy and momentum of this, and we have to equate it to the energy and momentum of this, but these are summed up. So this is not saying that PB has to be equal to this, PF has to be equal to this, and PC has to be equal to this. It allows many different combinations of values of PB, PF, PC, and also their energies. Okay? And it turns out that each possible outcome, each possible value of these contributes to the probability of it happening. But in this case, since there's a bigger difference in mass, you have more free energy to distribute to these 3 things. So you have more variety in the way that you can distribute it, versus here, where because the mass difference is smaller, you've got less energy to distribute among these 3 things. And so in general, the probabilities in this case are going to be smaller than the probabilities in this case. There's other reflections of the kinematic impact on these probabilities, but this is the one that you can actually kind of wrap your head around a little bit. Okay? And of course, in fact, as I said earlier, if we consider the process H, I, J, where MA is equal to the sum of these masses, then in that case, there's no freedom whatsoever in distributing this energy because the total energy initial is just fixed. And so the probability associated with that is 0. Okay, so the kinematics is going to play a role, and you'll see exactly what that role is when I write down the equations. What about dynamics? What do you think, what impact do you think dynamics has, or how does dynamics play a role? What is dynamics, by the way? I mean, you know what kinematics is? It's motion. We taught you this in Physics 1, right? We taught you about position, velocity, acceleration, and then we didn't say anything about Newton, because Newton requires forces. No forces yet. So we talk about kinematics, we talk about motion, and then we turn to dynamics by introducing forces. Exactly, yeah. Dynamics is more interested in the forces. And of course the forces involved are going to influence the probabilities, right? I mean, if I'm looking at the probability of an interaction that can take place via electromagnetism compared to an interaction that can only take place via the weak interaction, which do you think is going to be more probable? The electromagnetic interaction, because it's a stronger interaction. Okay? So this is going to rely heavily on forces. Okay. And it turns out that there is another degree of freedom, which is that in a lot of the processes that we'll analyze, we're going to find that we've got these things coming in and this stuff coming out, but there's myriad ways of connecting what's coming in with what's coming out with virtually existing particles. Virtually existing particles are, in many cases, force particles, but there are sometimes when you create virtual mass or virtual matter particles, and those are intermediate states. That's actually reflective of dynamics rather than this kinematics. This kinematics is purely external. Okay? All right, so here we go. Here we have the equations. Now, what's amazing to me is that in what I'm going to give you, these effects are almost separate. They're almost separate. They're really close to being separate. Like I can point to points in the equation and go, that's kinematics, that's dynamics, that's kinematics, that's dynamics. Okay? So let's do it. For decays, we have the following expression. So I'm going to imagine that I have M1 come in. I'm going to have come out particle 2, particle 3, particle N. And this is just, I'm not going to try and tell you exactly how this particle is decaying into particles 2, 3, and N. We'll learn about that later. But there are N particles that are going to come out of this in this particular channel. I'm going to assume that the particle that is decaying is at rest. I can always go to the rest frame of a massive particle as it decays. So I'm going to think about the rest frame. That makes all of the kinematics much cleaner and simpler. And so the decay that we're considering, I might write like that. All right. And we'll just call this the ith channel. Because remember, this is picking a particular outcome, and I want to calculate the decay rate. Okay? And then I would pick a different outcome and calculate the decay rate. And I'm just going to focus on one decay rate calculation, and then you can look at other outcomes if you want and put them all together and calculate the total. But here we go. Are you ready? Gamma I is S over 2 h bar times m1. That's our coefficient. Now let's finish it. Times an integral of some little thing I'm going to call m squared times 2 pi to the 4 times a 4-dimensional delta function
Okay.
over p1 minus p2 minus p3 minus dot 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 minus pn times a product from j is 2 to n of 2 pi times a delta function of pj squared minus mj squared c squared times a theta function of p0j times the measure of integration.
What is the measure of integration?
Yeah, that's about what I expected.
Yeah, it's about what you expected. Good, good. I'm glad to hear it. I'm glad to hear it. Okay, anyway, carrying on. So, no questions. Good. All right. So, for collisions, now, in all honesty, I'm going to write this expression, and then I'm going to go through and explain what all these terms mean. But I'm going to reflect the terms here with the terms that you're going to see here. They're going to have the similar terms. So I just want to get them both on the board before I go through and give you an intuition for it. So just let me write this down, and then I'll come back to it. So for a collision, yeah, I can do it. So for collision, we're considering two particles only being collided, and then we're going to have some outcome. And somebody trying to come in that door?
Someone just left.
Oh, okay. Oh, okay. Yeah, that's fine. And so we're going to have this outcome, and of course, you know, you can pick different outcomes, and you can calculate the cross section for different outcomes. And so, you know, if we want to write this. This will be the ith channel. And here we go. So the cross section for the ith channel is given by s h bar squared over 4 times the square root of p1 dot p2 squared minus m1 m2 c squared quantity squared times the integral of this mysterious quantity m squared 2 pi to the 4th delta 4 p1 plus p2 minus p3 minus p4 minus en times a product from j equals 3 to n of 2 pi delta pj squared minus mj squared c squared times theta p0j d4 pj over 2 pi to the 4th. Okay? These are called Fermi's golden rule. How many of you have heard of Fermi's golden rule? Okay. Yeah, and what Fermi's golden rule is basically doing is it's encapsulating all of the kinematic information in a process, leaving the dynamics hidden in one single term, m. Okay? Now, we're going to learn how to calculate m next time. So let me try and give you some intuition for what's going on here. All right? So hopefully you've written this process down so I can draw my connective arrows. So first of all, the M's in each of these encode dynamics. That is, this is where you're going to have the forces contribute. There's no forces in the rest of this. This is going to be influenced by virtual particles that are created and destroyed. Okay, that doesn't appear in any of this. All right. So the M quantities encode the dynamics, and unfortunately, they often depend on the exterior momentum. So I hope my labeling made this obvious, but perhaps not. This has a momentum P2, this has a momentum P3, and these are 4 momenta, so they include the energy and the spatial momentum. And this has a momentum Pn, this has a momentum P3, et cetera, and then this has a momentum P1, momentum P2, and this has a momentum P1, although it's in the rest frame, so it's kind of a simple version of the 4 momentum. So all of the P's that you see in here are the momenta of either what's coming in or what's going out. Okay? Now this is interesting because when we learn how to calculate M, we're going to be involved with internal virtual particles which themselves carry momentum. Okay? And we'll have to take care of that momentum, but more on that on the next lecture. For now, all of the momenta you see here are for the external particles, either things coming in or things going out. Okay? And if it's P1 and P2, or if it's P1 in this case, it's the incoming, and if it's any of these momentum, it's the outgoing. And here, P1 and P2 are the 2 incoming, and the rest are the outgoing. Okay, so let's get a vector. Joshua Muller. Yes. What do you think that delta function is ensuring us will happen? How comfortable are you with delta functions?
Fairly comfortable.
Okay. What is it going to force to be equal to something else?
It's going to be forced. It's going to force the integral to equal the rest of the stuff, right? Like, because when you integrate a delta function times a function, you just get back the function.
Yes, but you get back the function of.
At
So,
that one point, right?
so what do you want the argument of the delta function to be for it to be non-zero? Or contribute non-zero to the integral is what I might say. So if I have the integral of a function of x, delta x, dx, what is this equal to?
F of x. Like f of 0.
Yes, f of 0, because the delta function you can think of as it's 0 everywhere except wherever the argument of the delta function is 0. And then it takes a value such that the integral of this just gives you the value of the function at 0. So this delta function is really forcing its argument to be 0.
Right.
But think about it. Let's write down what that means to force the argument to be 0. We're saying P1 mu is equal to P2 mu plus P3 mu plus, what is that? What is that?
Is conserved.
That's telling you that the 4 momentum is conserved. Similarly here, this is saying that the sum of the incoming momenta has got to be equal to the sum of the outgoing momenta.
So why is that a plus? And then up there it's a minus?
Because here you have 2 incoming particles, so you have to add their momentum. Here you only have 1 incoming particle. Okay? So let's think about that for a second. Ostensibly, when you write this down and you're integrating over things, you're allowing all possible values. But this is saying, no, you can't allow all possible values because you have to have this be satisfied, and you have to have P1 plus P2 equals the sum of the outgoing momentum satisfied. The function is just hanging out to enforce the conservation of momentum. The total momentum coming in has got to be equal to the total momentum coming out. That's all it does. Okay? So we have that this enforces conservation of forward momentum. Yeah.
Maybe this is kind of dumb, but we have a 2 pi to the 4th over there, and then 1 in the denominator of like your integration constant. Why aren't we canceling those?
Well, the 2 pi to the 4th comes with the 4-dimensional Dirac operator.
Okay.
Don't worry why.
Okay.
Just take it as a given for now, and we can go over why later.
Okay.
Okay? And it has to do with the fact that you're in a higher number of dimensions. But don't worry about it.
So like, why aren't we canceling it out with the other 2 pi?
Oh, you can cancel them out, but the delta, so the thing is that you're, this doesn't really work by itself when you're integrating over functions of P1, P2, etc. You have to have the 2 pi forward in front of it. So we put it in there because it needs to be in there. Similarly, you have to have a 2 pi over 4 in the denominator here. Once you've accepted that, you can cancel them, but we're just trying to give the proper notation here. All right, so the next terms are these guys. And notice, this is literally just writing down a contribution from the momentum of each outgoing particle, because J only goes from 2 to n. So this is just over the outcoming particles. So you write it down for particle 2, write down exactly this. Then you write it down for particle 3, and you multiply them all together. That's all this is, okay? What do you think this term here and this term here enforce? Let me get the card. Joel, yeah, I must have not shuffled these. Joel, what is this delta function enforcing on us? So I should stress that all of the P's are for momentum.
So wouldn't that just be conservation of energy? Because it looks like something like that, because it looks like the norm you get from that one thing that I don't remember very well right now.
Ross?
It enforces the fact that the magnitude of PJ has to be equal to MJC squared. Right?
Which we call the
rest mass.
Which is a condition that we call the
On-shell condition.
the mass shell condition, or the mass shell relation. Okay. Now you guys might or might not remember this, but I'll refresh your memory. That's the 4 momentum, right? Where this is the relativistic energy and the relativistic spatial momentum. Okay, so if you do P mu, and I'm going to switch back to our old metric just for this example. Screw all this, we're going back to the old days. This would be minus E squared over C squared plus P dot P, right? But this is an invariant I can evaluate in any reference frame I want, so why don't we go to
The rest.
frame. In the rest frame, what is E? Say it loud, say it proud. It's MC squared, so we cancel that, we get MC, what's P?
0.
You're in the rest frame, 0. So this is M squared C squared. This is just enforcing that this relationship holds, that the square of the 4 momentum is equal to M squared C squared. That's the square of the 4 momentum, that's M squared C squared. This is what we said that real particles have to satisfy. This is forcing them to satisfy it. Okay. Because remember, you're integrating over the momentum. The integral gets all the contributions, and this is just saying, nope, 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 you can only contribute to this integral if the magnitude squared of the 4 momentum is equal to mj squared c squared. Of course, you still have a lot of flexibility in how the momentum is distributed among its components, okay? But it is a constraint. And then we have a step function. How many of you are familiar and comfortable with step functions? What is the step function? Yeah, it's not a direct function. It's, you know, theta function of 0 is 0, and then it becomes 1 after you pass the point 0. What is the step function guaranteeing us? Oh, let me draw a card. Sorry. Oh, Sarah. What is that step function guaranteeing us? So this is a step function. It's 0 until you get to the argument of the step function being 0. I should say this is,
Such a certain momentum.
yeah, that should be an
So
X.
that's initial momentum, but what's,
Well, no, this isn't. This is the 0th component of the 4 momentum.
okay.
What's the 0th component of 4 momentum?
E over C.
Yeah, so this is guaranteeing that the only contributions are those when the E over C is positive. That is, this is insisting that the energies of the particles coming out are positive, not negative. Again, you might go, well, who would put negative energy particles into their calculation? Well, you're integrating over D4PJ. The contributions to this integrand include negative energy contributions, but you're going to wipe them out with this theta function. That's all the theta function's doing.
Why does
Okay?
it include those then?
Well, because this is just a stupid integral measure.
Okay.
I could say, you know, smart integral measure and then ignore all this, but we can't do that. We can't do that.
All right.
Okay? So, so this one forces the mass-shell relation or condition, forces E greater than 0, and then this is just, you know, this is just the measure for the integral. Okay? So have you got at least a sense? I mean, we didn't derive this. We're not going to derive it. Don't worry about it. And we won't do a ton of calculations with it. But at least is there a sense of the interpretation of the various elements in these expressions? And this is why I say most of what these expressions are doing are they're telling you explicitly how kinematics impacts the answer. You know, how momentum, you know, it's not telling you crap about forces. That's completely contained in M, which I haven't even given you the form of yet. We're not even going to talk about M until next time. Okay? Now, and you know, a lot of coefficients are not that important, but this S seems to be important. It's common in both factors. And so I'll give you an interpretation of what S is. S is 1 over S. Huh?
You just said S is 1 over S.
Yeah, 1 over S. You guys don't be jackasses. 1 squared, or sorry, S1 factorial, S2 factorial, dot, dot, dot. Remember Sn factorial. And my numbering scheme is not good here, but it doesn't matter. Where S1 is the number of identical outgoing particles of type 1. So what I have in mind here is, if it doesn't matter if I'm doing a decay or a collision. It's the same thing. So if I'm doing a decay, and I have, you know, particle A, it's going to decay, and it's going to decay into, well, here's one channel, particle B, particle B, particle B, particle C, where these 3 B's are all the same, and these 2 C's are the same particles. Then calculating the decay rate involves a factor of S, which is going to include 1 over 3 factorial times 1 over 2 factorial, because I have 3 and I have 2. Okay. Yeah.
Just for clarification, is that Fermi's golden rule, or is Fermi's golden rule something else, right?
No, Fermi's golden rule are these.
Okay.
Sorry, yeah, no, Fermi's golden rule applied to the entire board, not just what I've got underneath it. Yeah. And all that this is saying is you can't distinguish these three particles, but when you initially do the calculation, you're treating them like they're distinct. Like if this gets a certain amount of momentum and this gets a certain amount of momentum, that's completely different than if this one gets the amount of momentum that this one got and this one gets the amount of, but actually it's the exact same outcome. So this factor is just removing that redundancy. Okay? And it's literally, it's this, probably the simplest part of this calculation, because you're like, oh, 2 electrons coming out, 1 over 2 factorial. Done. Okay? And if you're not comfortable with that factor or what that means, we can talk more about that later. Okay, so, all right. Now, to finish up, we are going to take this and we're going to bang on it just a little bit, because it turns out that at present, you can't do the integral. Why can't you do the integral?
You don't know what M is.
Say it again?
You don't know what M is.
Yeah, you don't know what M is. And M is going to depend on the momenta.
Yeah.
So you're integrating a function of the momenta, and you can't do the integral until you know it. Except, unless you can miraculously use the delta functions to just replace certain values of the momentum here and evaluate the integral. And it turns out that there's 2 really simple circumstances where you can do that. Okay? So let me go over what those 2 circumstances are. And then we will end for today, and when we come back, we'll actually learn how to calculate M. And this will get our hands dirty with Feynman. Good old Dick Feynman. His name is Richard. But anyway, okay, so here we go. So first of all, I'm going to break down some stuff. So first of all, we can always do the following. We can always take the integration measure d4pj, this is just over 1 outgoing momentum. All right, and when I write d4pj, you can think of this as d0, or dp0 times dpx times dpy times dpz. I'm just short notating it as d4pj. But if I write it like this, this is just picking out the time-like piece and then leaving the spatial pieces labeled with a vector arrow, so you realize that these are not still the 4 momentum p, but they're the spatial components. Then we can do the following. So first of all, if I take this integral, or sorry, this delta function, and I break pj up into its spatial and time-like components, then this is going to become, and remember we are now using the metric convention that the time-like piece in the quadratic gets a negative, a positive, and the spatial pieces get the negative. Okay. So I just took the 4 momentum and squared it. That gives me p0 squared minus the spatial momentum squared. Before it would have given me minus p0 squared plus pj squared, or p squared. But we're now adopting the new metric convention that the metric is 1 minus minus minus. Okay? And now we can use a little trick. If we have delta x squared minus k squared, where x is a variable and k is a constant, then we can also write this as 1 over 2k times the quantity delta x minus k plus delta x plus k for k greater than 0. Okay? as just an identity satisfied by the Dirac delta function. But if we think about it, if I call this thing k squared, and I call that x squared, then I can take this expression and I can turn it into delta functions over linear terms. Of course, I have to divide by 1 over 2k, which is going to be the square root of this thing. All right? So here we go. Let's plug that in here and see what we get out of it. S over 2 h bar m1 times the integral of m squared, 2 pi to the 4th, delta 4 p1 minus p2 minus p3 minus pn, product over j equals 2 to n of 1 over, I'm just rewriting this using that expression, 1 over 2 times the square root of the vector momentum squared plus m squared c squared times now d3 ej over 2 pi cubed. Okay. And then similarly for the sigma I can rewrite this in the following form. And this isn't the end of it. I'm actually going to consider scenarios where these are actually very useful. But the thing I want to stress right now is what I've done up there, I can do in any of these expressions. So I'm just rewriting these expressions. I haven't picked any particular circumstance to apply it to yet. Okay? And now is where we're going to see a little bit of magic. If we, in the decay case, assume a two-body decay with M1 at rest. Okay? Now, this expression right here is not assuming that we're in the rest frame of mass 1. I mean, otherwise, why would I be writing in P1? If you're in the rest frame of mass 1, P1 has a very specific form. Okay? So these expressions are for any motion of the first mass and then the consequent motions of masses coming out. But if I assume, first of all, that I have one particle come in and two particles come out, and that I'm in the rest frame of this, then I can use this expression to completely evaluate the integral. And the answer comes out to be, whoops, SP over 8 pi h bar m1 squared c times m squared. Now, if you want to fiddle around with this and you want to actually take this and consider the details of this, you're happy doing that. I'm not going to force you to do that. Okay. But the tricky part is that this is an integral over the 3 spatial momentum. Okay, so applying this 4-dimensional delta function is not completely obvious and simple. All right? But nonetheless, what this means is that I can, once I've got m as a function of p, I can use the delta functions over here to evaluate the integral just by plugging in certain values of p into the m. Okay? So S is still the redundancy factor that we had before. You know what all these things are. What about P? P is C over M1 times the square root of M1 to the fourth plus M2 to the fourth plus M3 to the fourth minus 2 M1 squared, M2 squared, minus 2 M1 squared, M3 squared, minus 2 M2 squared, M3 squared. That is, this is the momentum of either outgoing particle. This is the spatial momentum of either outgoing particle. It doesn't matter which one. Why doesn't it matter which one? Draw a card. Dylan.
If you know the momentum of one, you know the momentum of the other, because
B.
they add up to the original
Yeah, exactly. And the original spatial momentum was?
0.
0. Yeah, exactly. Okay? So, and you're taking the magnitude of it. So if one's positive, it doesn't matter. If one positive, the other's negative, it doesn't matter. Okay? Any questions? All right, so, and then for scattering, it turns out that if we consider two-body scattering, and you can kind of imagine where the rest frame was used here, because it gave us a very specific form of P1, and then we can just use the delta function, everything simplified. What do you think we're going to have to restrict this to? What frame do you think we're going to have to restrict this to? Ross?
The center of momentum frame.
Yeah, the center of momentum frame, because what's the total spatial momentum in the center of momentum frame of the two particles coming in? What about two particles going out? I saw that. It's good. It's good. Yeah, it's 0. Okay. So for a two-boundary scattering in the center of momentum frame, we find, and I'll just go ahead and give you the more powerful differential cross-section. D sigma d omega is h bar c over 8 pi squared s m squared over E1 plus E2, so E dot epsilon squared times P final over P initial all right. Notice E1 and E2 are not necessarily masses because these things have energy coming in, but they're in a zero total momentum frame. What do you think P final is? It's what?
Final momentum.
Of which particle?
Whichever one you're talking about up there.
Which particle?
Either?
Either of them. What's the total spatial momentum of the particles coming out? 0. So I can use the spatial momentum of particle, I didn't draw the process, 2, or I can, no, sorry, I didn't draw the process. So I got 1 coming in, I got 2 coming in, I got 3 going out, and 4 going out. So I can use the momentum final of 3 or 4 because they're equal and opposite, because the total spatial momentum is 0. Okay, the total 4 momentum is not 0, the total spatial momentum is 0. And similarly, P initial is the spatial momentum of either of the particles going in. Okay, again, because they add to 0 for the two-body case. All right? So again, like, you don't have the final answer because you need to know what M is. All right? And M is a quantity we're going to learn to calculate next time, and it will often involve the P's, which means when you evaluate this, you have to actually plug in values of P. Okay. But there's no integral left to be done. This is rarely the case. Most of the time, you will have to do an integral. There's no getting around it, okay?
Will we have to do an integral, or will Mathematica have to do an integral?
You won't get Mathematica doing integrals in this class. In fact, I think the only integrals I'll actually ask you to do in this class will be delta function integrals, the easy ones. All right, that's it for today. When we come back next time, we're going to get high on the ABCs of the Feynman diagram.